Okay. So, everyone got their test 2 back? Pretty good test for pretty well, everyone. Okay. I posted the solutions on Moodle if you want to have a look. Oh, I forgot to bring them today, but I've got some blank ones that you can grab for practice, but I forgot to bring them today. Sorry. I posted the marks on Moodle. I don't want you to get too hung up on the grade that's posted on Moodle. It's not very clever. It doesn't know what it's doing, partly because I haven't put in the time to set it up. But even if I had set it up, it wouldn't be able to do it properly anyways. So yeah, it's like weird. So don't look at that grade. Just look at your individual grades. Right, I've given you the grade breakdown. Do you guys know how to calculate your grades? Or is it just kind of a secret thing that goes into Moodle and something comes out?
Literally waiting to get my diploma and let them tell me if I failed.
How about, I'll just show you quickly how to keep track of what your grade is, because I think it's a valuable skill, and I guess it is math after all. So, what's my grade? However, am I supposed to know what my grade is? So I give you the grade breakdown, right? And so let's say, well, ours is a little complicated. Let's say we just have 3 things, right? So we have a test worth, let's say 50% of our grade. We have an assignment worth 10% of our grade, and a final worth 40% of our grade, right? This, of course, has to equal 1,000%. No, 100%. So let's pretend that we have 2 assignments. So they're 5% each, right? So the first thing you need, right, is the grade breakdown. Of course, when I'm saying that if you get a higher grade on the final, then I'll put the weight of the test on the final, right? That'll have to be adjusted for, but just in general, just to know where you're at, right? You can say, okay, well, here's the item that you handed in. So let's say your test, and let's say what your grade was. Okay. And then you need to know the weight. Oops. And then you can find the total. Okay. One of the grades and the weights has to be a percentage, and the other one has to be a decimal. Okay. I always do the grade as a decimal, and then the weight as a percentage, doesn't matter. Okay. But let's say that my grade on the test, I got a solid 80%. Nice. So 0.8. Okay. Remember, the test has a weight of 50%. What you do is you just multiply across here. Right? And so 0.8 times 50 means I have 40% of my grade overall. Right? That's a nice chunk of change. And then I did assignment 1 and assignment 2. I got 65% on assignment 1, and then I pulled up my pants and I got 100% on assignment 2. How about that? In my hypothetical scenario. Oops, not as a decimal. like I said, I switch between the decimal and the, doesn't matter. So I have 0.65 of 5%, right? So times 5. So that assignment gave me 3.25 out of 5 of my total grade, right? And then I got this whole 5, right? If I add this up, right, this total is out of 60. So if I want my grade before the final, right, I would do 40 plus 3.25 plus 5 out of 60, right? So what would my grade be then? 40 plus 3.25 plus 5. So then out of 60, I have 80.4%. Right? But here's where you can kind of play around and see what you need to get on the final. Right, the weight is 40%. If you want to have some desired total grade, right? So you can kind of backtrack. Hopefully that kind of makes sense, right? But so you need to know the weights, and that's why I give those to you. You need to know your grades. That's why I hand everything back. You can kind of keep track of where you're at. Right? Nice. Moodle's not such a mystery anymore. Okay. Oh, what were we doing today?
Math and
Nice.
Yeah.
Sure, let's do some math. All right. So today we're going to start chapter 6. So chapter 6, we start getting into annuities, which is the back page of our formula sheet. Okay. We're going to make our way through a lot of these formulas today, even though it might seem like a daunting task. Okay. But what you'll find is that on the left-hand side, that's going to be chapter 6, basically. And on the right-hand side, that's going to be chapter 7. So annuities, let's talk about what annuities are for a second. Annuities are when we've got regular payments, right, either coming in or going out, right? Think loan payments or a loan repayment plan, right? We've just been dealing with, oh, so we make a payment at a year and then we make a payment at 3 years, right? Not regular intervals. So now we've got all these payments coming in at regularly scheduled intervals, right? And so we need to be able to deal with that. Okay. Pardon? Yeah, so basically everything you sign up for, like a monthly payment plan or repayment plan, is going to be an annuity. Okay. So chapter 6, here we go. Feels weird with no review, but oh, I saw some beautiful timelines on this test. I was pretty pleased, I did mark it. I was gentle with the marking, let's say. But overall, I was really impressed with how you guys handled that test. There was one little curveball. It was unintentional, and yeah, could I have fixed it for you guys? Yeah, but I wanted to see how you handled it. What? That's so mean. Well, it worked out for a lot of you. Question 4, the long answer, where you're comparing two interest rates, right? Your compoundings worked out to be 17.3 repeating for option 2, right? And so if you left it as that, I didn't dock any marks, right? But if you remembered to round up to 18, right? Because we can't have 0.3 of a compounding, then I gave you a bonus mark. So I didn't take any marks off if you didn't round, but I added a mark if you did, because I thought that was pretty impressive. But a lot of you guys did it, so I don't know, I'm gonna congratulate myself as well for teaching you that. So okay. Oh, any questions about the test before we get started here? No? All right. Annuities. So with these payment plans, let's call them annuities, right? We're gonna have some number of payments, right? And then we have our number of compoundings. Okay, so in our calculations, those have to be at the same time. Okay, so what we're gonna develop first is how we can adjust our compoundings and change the compounding frequency. Right, so we're going to talk about effective rates and then equivalent rates, and the equivalent rates are going to be the more important ones. Okay. Where we can just move from compounding quarterly, let's say, to compounding monthly, and they'll be the same. We've done that already, right? What rate would be equivalent to these two rates over some period of time, right? You did that on the test, right? So we're just going to develop formulas for doing that first. So 6.1 is on effective and equivalent interest rates. So an effective rate is the annually compounded rate that gives you the same future value as whatever your original rate was. Okay. So it just converts always to annual compounding, right, where the F is 1. So the effective rate which we denote I subscript F, rude, the annually compounded rate. So this is going to be the annually compounded rate that produces the same future value as the given nominal rate, aka the given nominal rate, meaning R and F. Right, so I've been giving you 6% compounded weekly, right? What is 6% compounded weekly? The effective rate would give you that as an annual compounding. So on our formula sheet, right, we're going to plug away at these formulas. That's how this class goes. Right, in the beginning, we have to introduce all these formulas, and then we're able to work through and plug through examples. Right. So the first one gives us the effective rate. Okay. Effective rates are usually just kind of short answer questions, right? But we'll get them out of the way first. So we use the effective rate (1 + I) to the power of F minus 1. And this is on your formula sheet. Yeah, the effective rate. Okay. This is a periodic interest rate, right, I, but because the F for this I is 1, right, it's kind of floating between the two. Okay. So where I is the periodic interest rate. Periodic interest rate. And F is the compounding frequency. just as before. So those definitions aren't new, but it's just emphasizing that they're going to be the same. So let's do a little example, example 193 here. Whee! No, it's the compounding frequency. Oh. Maybe if I start over here, I can catch it all. It's all wavy. What is the effective interest rate of an investment which earns 4.8% compounded quarterly? Okay. So we're just wondering, what's the effective interest rate? So what are we given? We're given that R is 0.048. And the frequency is quarterly, so 4, right? And we have to find the effective interest rate. So then we can just use our formula. The effective interest rate is 1 plus I to the power of F minus 1. So, yes?
Why in the heck are we doing +1 if we're just going to minus that one after?
Because the 1 is inside the brackets being powered to F. So it's not necessarily, I mean, 1 to the power of anything is 1, but it doesn't disappear. Yeah. Okay, but good call. All right. So we first have to find I, right? You can do it inside the formula if you want, right? So we know that I is just R over F. That's the one we've been using all along now for compound interest. And so we got 0.048 over 4. Thanks. Or if you want to start putting it into the formula here, right? Just rewriting I as R over F and then plugging it in, that's fine by me, right? You just don't want to forget anything. So often I'll like to do stuff on the side, but sometimes I get lazy and just plug it in. It's up to you. Okay. So now we have 1 plus 0.012 to the power of F, which is 4, minus 1. Oops. I'll do it on, thank you, but too long. 1.048870933 minus 1. Don't forget that minus 1. 0.048870933. So what does this mean? It means that an annually compounded rate of 4.89, right, is going to be the same, right, or equivalent to 4.8% compounded quarterly. Right? That's what we're saying here. So therefore, a rate of 4.89% compounded annually is equivalent to 4.8% compounded quarterly. Just as a check, right, when you're doing these questions, these are gonna be very similar, right? So if you're finding things that are kind of way off, then maybe check your math because they will be pretty similar, right? Regardless of how you're compounding. We even saw that with the continuous compounds, right? Continuous compounding to a year didn't really make that big of a difference, right? So that's just a quick check that you can do to make sure you're on the right track. So that's that formula. The special case, like I said, is the continuous compounding, right? Taking up 3 formulas on here. What a waste. For this little tiny special case, we have to have this special formulas. In general, if you see an E in there, it's going to be attached to continuous compounding, right? Just like you saw in the future value formula, the one with the E is the one you use for continuous compounding, right? And so here, when you have the effective interest rate with the E to the R minus 1, that's going to be if you're going from continuous to an annually compounded rate. So if we have a continuously compounded rate, so if we have a continuously compounded rate, sound like someone wanted to get in but changed their minds. Continuously compounded. Oops. Thanks. Compounded rate. Then we use the effective interest rate is E to the R minus 1. And this is on your formula sheet. So we could have used this formula for that example that we did maybe a week ago, finishing off chapter 5, where R is the nominal rate. Yeah. Oh, because the effective interest rate is the annually, yeah. So it's like it's a special case. I'm not even 100% sure why we bother with it, to be quite honest, because we'll be able to move to an annually compounded rate if we want to, but it's in the textbook, so I'm going to cover it. But yeah, the effective rate is just a special case where we're always just moving to the annual compounds. So let's do a little example with the continuous compounding. We'll do example 197. An investment earns 6% continuously compounded interest. What is the effective rate of interest? Right. So R is 0.06. And I'll just make a note here, continuous. Right, so there is no F. So the effective interest rate is E to the R minus 1. Nice fun formula. Right, really kind of quick. E to the 0.06 minus 1. 0.06 on your screen, and then second log gets you e to the x. So you get 1.0618365547 minus 1, which of course gets you 0.0618365547. So then, oh.
Hit 0.06 and then hit the EBS. Oh, hold on.
Got it. Nice. Yeah, make sure that that's what you're getting, right? because we're not too familiar with the e to the x quite yet, but so what's that saying? 6.18% compounded annually, right, is the same as 6% continuously compounded. So not, again, not that big of a difference. Even if we're going from continuous compounding, where it's just continuous, always compounding, right, to annual compounding isn't that big of a deal. Oh, because it's asking for the effective rate. So this is just by definition, yeah, annual compound for the effective rate. Oh, compound. Oh, whatever. Okay. So therefore, a rate of 6.18% compounded annually is equivalent to 6% compounded continuously. You'll squeeze continuously in there. Continuously. Yeah. So, like I said, this is a special case, right? But let's start talking about equivalent interest rates, right? So moving from quarterly compoundings to monthly compoundings, right? How do we make these adjustments?
Are these all similar to being the same?
Yeah, but this is a special case, right? Because the effective interest rate is always just going to move to an annual compounding.
Oh,
Right.
okay.
So now, if we want to move to something other than compounding, let's make a note here. So if we want to find equivalent rates and move to something other than compounding annually, oh, annually. Bless you. Right, F equals 1, but it's also the, bless you, the effective interest rate. We must use equivalent interest rates. I know that's not very helpful. Right. What is an equivalent interest rate? So equivalent interest rates, there are going to be two interest rates, right, that yield, they have the same effective rate in theory, right? If you move them to their effective rates are going to be the same, right? So regardless, they're going to yield the same future value, right? But I think if I just said equivalent rates, we all understand that, right? So definition doesn't help us that much. So two interest rates that have the same effective rate. That's the definition, but we just look at the word equivalent, then we kind of get it.
So really, it shouldn't matter like a whole lot what the two different rates are, as long as they have the same, the IEFF.
As long as they have the same effective rate, right? So if we use this fact that they have to have the same effective rate, we can develop a new formula for moving between one F to another F. Okay. So, oops. Effective rate 1 has to be the same as the effective rate 2. Right? This was just by definition. Right? They're equivalent if they have the same effective rate. Okay. So now if we substitute the formula for the effective rate into each of these sides, right, then we can solve for one of those i's, right? We're gonna have subscript 1s and subscript 2s. So if we write this out, we get 1 plus I1 to the power of F1 minus 1 is equal to 1 plus I2 to the power of F2 minus 1. Right. Just taking that formula for the effective rate and just distinguishing between group 1 and group 2. Just to match the formula sheet, we can solve for either I1 or I2 because we want to move to, so we want to move from this frequency to this frequency, right? So what we really want to know is we want to know I2, right? So we're going to solve this formula for I2. So solve for I2. Okay. All right. Nothing to it but to do it. I'm not scared. All right. So we're going to add 1 to both sides. Right. I'll show all my work. Minus 1 plus 1. So 1 plus I2 to the power of F2. Okay. These are going to go away. Right. And then, so if we want to get rid of that to the power of F2, right, we would take the F2th root of both sides, right? So we end up with the F2th root of 1 plus I1 to the power of F1 is 1 plus I2. Whole lot of good that did us. It's okay, we have our exponent rules that we can use, right? So we know that to take the F2th root, we would take 1 plus I1 to the power of F1 to the power of 1 over F2, right? So we would have 1 plus I1 to the power of F1 all to the power of 1 over F2. Because that's the trick that we use to take any square root, or not square root, any root of whatever we want is 1 plus I2. Okay. Remember the rules of exponents say that we can multiply these, right? Combine these because they're on the same level. And so that's how we get to 1 plus I1 to the power of F1 over F2 is 1 plus I2. Now to solve for I2, we just subtract 1 from both sides. 1 plus I1 to the power of F1 over F2 minus 1 is I2. And that's exactly what's on your formula sheet. Right. Second one on the left-hand side. So I'll just write that down. So I2 is 1 plus I1 to the power of F1 over F2 minus 1. That's on your formula sheet. So this gives the new periodic interest rate, right, I2, with a compounding frequency F2 from the old I1 and F1. So I use those subscripts to denote, okay, so I had a rate of 4% compounded quarterly, just to keep things simple, right? So then my I1 would be 0.01, right? And then my F1 would be quarterly, so 4. And then if I want to move to monthly compounding, my F2 would be 12. And then I can calculate my new periodic interest rate. Nice. So we're going to use that one a lot. Okay. So really the effective interest rate is just a special case of this where F1 is just, or F2 is just 1, sorry, right? You're moving to an annual compounding always. All right. Let's do a little example. 198. Doo-doo-doo. An investment earns 5% interest per year compounded semi-annually. How much interest should alternative investments, which are compounded quarterly, pay? So here, let's give, because we're going to move from a rate of 5% compounded semi-annually to something compounded quarterly. Right? So we know that R1 is 0.05 and F1 is 2, right, semi-annually. R2 we don't know, but we know that F2 must be quarterly, 4. So we can use our I2, our formula for I2, right, to figure out the periodic interest rate, and then we can convert that to R, right, the way we have been doing. So I2 is 1 plus I1 to the power of F1 over F2 minus 1. I guess I should have found, I'll sneak in I1 up here. I1 is 0.05 over 2, which is 0.025. So I have 1 plus 0.025 to the power of F1 is 2 over F2, which is 4, all minus 1.
Someone please turn off their phone.
There's a buzz up here. So, even though we can do 2/4 in our heads and just kind of simplify it that way, right? I just always do it in my calculator, right? Because sometimes it's going to be a little bit harder, right? Moving from biweekly to daily, for example, gets a little messy. Right? So here, we're going to have 1.025 to the power of 2/4, all minus 1. Sounded happy though, so it's good. Here, I'm gonna show you how on your calculator. So on your calculator, you're gonna have 1.025 on your screen, and then hit the Y to the X button. And then I put brackets around it just to be sure. And then equals 1.025 to the power of 2/4. Oops, I forgot my brackets. I make a big deal about brackets and then I don't use them. So I get 1.012422837. So make sure you get the same thing for that power there. So we have 1.012422837 minus 1. Don't forget that minus 1. It's going to make a big difference. 0.012422837. Nice. So that's your periodic interest rate, right? But just like we were doing before, right, if you have to solve for R, then I is still R/F. And if I is 0.012422837 equals R, which is what we're trying to find, the frequency of the second rate, right, is 4. So now if we multiply that by 4, we have an R of 0.049691346. So therefore, a rate of 4.9, let's say 7%, compounded quarterly is equivalent to, what were we dealing with here? 5% compounded semi-annually. Compounded semi-annually. Did you get to the bottom of what's going on out there?
He was yelling. She's like, fuck. I was like, oh, okay. She's like, sorry, I'll try to clean my phone.
So we still don't know what it was about? Oh, I'm so curious. Did you get to the bottom of what's going on out there?
No.
Yeah.
I think they canceled class next door.
They're upset? I mean, it sucks if you make the trek, but thanks, Kevin. Yeah. Appreciated by all. Okay. So just like before, we have the special case where we're moving from continuous compounding, right? Continuous compounding, there is no F1. So then we have to have a special case, right? So for continuous compound, for continuously compounded interest, we can convert to a different compounding frequency. F2 by using the formula I2 is e to the power of r over F2 minus 1. Of course, this is on your formula sheet. So continuous compounding isn't, going to be that common, but because they are these special cases, they get their very own formulas, which is kind of annoying, but now we know how to deal with it, right? So R again is that continuous compounding rate, and then F2 is the one that we want to change it to, right? So, oops. I'll just, oh, did it again. Do. Where F2 is the desired compounding frequency. Just emphasize that. Compounding frequency. Of I2.
Be switched if it was I1 and
well, we're gonna use, yeah, I mean, in theory, but what I want you to get in the habit of doing is using the 2's for the new rate. So 1's for the old rate, 2's for the new rate. No, it works, but I like that kind of 1's for the old rate, 2 for the new rate. So same idea, right? If you want to go from some compounding to a continuous compound, right? We have a way to get back to continuous compoundings, right? And so, or we can convert a given rate to a continuously compounded rate by R equals, and on your formula sheet, we have F subscript 1 times the log of 1 plus I1. In the textbook, oops. In the textbook, it just says R is F times the log of 1 plus I. I don't like that one as much, right? I just kind of, but they're the same, right? But I just prefer the subscript notation saying that, okay, well, I want to move from this compounded to a continuously compounded, right? So from this to the continuous rate R, right? So that's why this is the one on your formula sheet. But if you're looking through the textbook and kind of working through with those problems, then it just uses that formula. But I think we can all agree that they are the same, right? Just one's more thorough than the other. Let's do example 202. An investment earns 5% interest per year compounded quarterly. What is the equivalent continuously compounded rate? Right? So we want to move from compounding quarterly to a continuous rate. So we have to use the R equals F1 times the log of 1 plus I1. Okay. But first we want to have, so R1, yeah, times the log. That's okay. So we have the R1, 0.05%, and F1 is compounded quarterly. And before I forget, I'll just calculate I1 is R1 over F1, 0.05 over 4. Let's call it 0.0125. So now we can use the formula R equals F1 times the log of 1 plus I1. Oh yeah, no minus 1. F1 is 4 times the log of 1 plus 0.0125. 1.0125 log times 4. So I get 0.0496908. So make sure, yeah, that's what you're getting. So what does that mean? It means that a rate of 5% compounded quarterly is equivalent to 4.97% compounded continuously, right? Or vice versa. So a rate of 4.97% compounded continuously is equivalent to 5% compounded quarterly. Nice. Let's do one of the other case too. Example 203. So little. What monthly compounded rate is equivalent to 9.5% compounded continuously? Right, so now we have a continuous rate and we want to move to a monthly compound. Right? So we have R is 0.095, right, where R1 and F1 is continuous, so it doesn't really exist. And R2 is the one we want to find, where F2 has to be monthly, so 12. So we're going to start by finding I2. So I2 from a continuous compound is e to the r over F2 minus 1. So we have e to the 0.095 over F2, which is 12, minus 1. 0.095 divided by 12 to the power, e to the power of that. I'll just subtract 1 right away because it doesn't matter. 0.007948086. This is the periodic interest rate. right? So this is each month. So we have to find R2, bless you. So find R2. We know that I is R over F. So we have 0.007948086 is R over F, which is 12. Point 0.095377036. So 9.54% compounded monthly is the same as 9.5% compounded continuously. Therefore, a rate of 9.54% compounded monthly is equivalent to 9.5% compounded continuously. Nice. Looks like it's not working. Is everyone getting that? Same rate. Are you doing e to the power of it?
Yeah, so 0.195 divided by 12 equals, so the second equals, and then minus 1. I finally got the right number. I got 1 3 times.
Just had to talk it out. No, it's my attention. It makes all the answers just kind of reappear suddenly. It's really annoying. I know. As a student, been there. Like, it wasn't working for like an hour. And now I did it and it's working. So I don't know what happened. Anyways. No, don't worry about it. Okay. So these are skills that we'll need, especially that finding I2, right? So especially this I2 is 1 plus I1 to the power of F1 over F2 minus 1. We'll be using that one quite a bit. Okay. The reason being, like I said in the beginning of class, is that because now that we have these regular payments, right, and we're going to have some compounding frequency, they have to be at the same time, right, for our math to work out. Okay? And so because we can't adjust the payment schedule, we have to adjust the compounding frequency, right, to match the payment schedule. Okay. So let's talk about actual annuities. 6.2 annuities. We've already kind of talked about it, okay? But you'll notice it takes up a huge section of your formula sheet. That's because there's different types of annuities that we'll talk about. Okay. So an annuity is a series of equal payments at regular intervals. So we're going to define some things that we already know, but we'll put them on paper and then we can forget about it. The payment interval is going to refer to the amount of time between the payments. The amount of time between payments. The periodic payment, right, is the amount of each of these equal payments, right? So at each payment interval, the amount that you're paying. So the periodic payment is the amount of the equal payments I have in the annuity. Don't really need it. It's going to be denoted by capital PMT. Oh, we've seen that already. Right on your calculator function, there's a PMT button. We've been leaving it at 0 for now, right? But now we can start filling it in, and then we can have the payments per year as well as the compoundings per year, right? So that's where they'll come in. Okay. And then we'll just define the term is just the duration of the payments, right? So the duration of the payments. Right. So you buy a car and you've got a, I don't know, you get a loan for 5 years, 3 years, 8 years. Yikes. Right, same thing with mortgages, 20 years, 25 years. The glory days of 30 years they've come and gone. I think you were able to get 30-year mortgages for a while. Not anymore. So, anyways, that's the term of the payments. All these things we kind of know just from life. Okay. One curveball for annuities is that N is now going to denote the number of payments that we're making, right? So N has denoted the number of compoundings, right? Now N is going to denote the number of payments. But remember, we have to match our number of compoundings to the number of payments. So technically, they'll be the same, right? But we have to start thinking of N as the number of payments instead of the number of compoundings. So F is the compounding frequency still. Yeah. So when discussing annuities, N will now denote the number of payments. Yes. Do you want M? M is probably taken. It's a pretty hot letter. So, annuities, right? There's different types, right? So we'll start with ordinary annuities and then annuities due. Ordinary annuities are where the payments are being made at the end of the payment period, right? So at the end of each month or at the end of the day or at the end of the year, whatever, right? Whereas an annuity due, the payments are being made at the beginning, right? So imagine that you're putting into a savings account, right? It's always nicer to have savings than paying off a loan, right? So you're putting in money at the beginning of the year versus at the end of the year, just an extreme example, right? At the beginning of the year, it's going to sit there and earn interest for that whole year. Whereas at the end of the year, right, at the end of the year, you just have what you just deposited, right? And so the difference in value, putting it in at the beginning of the term or at the end of the term, sorry, not the term, the payment period, right, is going to make a difference. And so we need formulas to take that into account, that little bit of extra time that it's sat in the account, right, by making the payments at the beginning. But that's going to be chapter 7. So once we've done chapter 6, we basically do it all over again, but with the payments at the beginning. All right. So that's what I like about chapter 6 is from here on out, we basically just do the same thing, different tweaks along the way. Okay. So, and then another layer, okay, is we can have just what we call simple annuities, where the payment frequency and our compounding frequency, they're the same, right? So that's a simple annuity. And then we can have a general annuity, which is more common, where the payment frequency and the compounding frequency aren't the same, right? And then we'd have to adjust our compounding frequency to match the payment frequency, right? And that's why we had to learn what we just learned about the equivalent interest rates. Okay. Oof, that's 6 and 7 in a nutshell. Let's pack it up now. But I still haven't figured out a nice way to make this tree diagram, right? Because at the top we've got annuities, or an annuity, and it can be either an ordinary annuity or an annuity due. And then each of those can be either a simple annuity or a general annuity. So instead of doing that, I'm just going to do two trees, and then you can mix and match. Still haven't figured it out. Nothing beautiful. But if you think of something, how to map this out, let me know. Because what's the twist? We could have an ordinary general annuity, an ordinary simple annuity. We could have a simple annuity due, a general annuity due, right? So those are all the different types that we need to figure out how to deal with. Right? For better or for worse, they're all very similar, right? So we have, just in general, an ordinary annuity or an annuity due. Put a little description underneath here. So payments are at the end of each payment period. Which is kind of the default, right? So we'll start with ordinary annuities, and then, like I said, in chapter 7, we'll move to annuities due, right? But I would have to tell you that, okay, starting today, you're going to make a payment at the beginning of each week, right, for an annuity due. So payments at the beginning of each payment period. And they can be either a simple annuity or a general annuity. So a simple annuity is where the payment they've got payment period, sure. Payment period coincides, right? Same as, so I'll put in brackets just in case. With the compounding period. And a general annuity, right, is where the payment and the compounding periods are different. Payment and compounding periods are different. So we'll just make our way through these, right? Solve for all the things we can solve for, right? Kind of dissect all these formulas. Okay. One thing you'll notice, right, is that there's no formula that has both the future value and the present value in it, right? And so we'll either know the future value or want to know the future value, and so we have to pick the right formula, or we'll know the present value or want to know the present value, and then you have to use the present value formula, right? So they're not in the same formula anymore, which is why we have two more formulas for n, right? Depending on if we know the future value or the present value, right? So just the fact that they're not in the same formula anymore doubles the number of formulas that we'll need, right? But as long as we know what we have and what we're looking for, then we're safe. So let's start, right? I said the default is going to be ordinary annuities, right? Just payments at the end of each payment period. And unless I specify, you can assume that the payments are at the end. And then we'll start with simple annuities. Sounds reasonable enough, right? Even though we could do general annuities right away, because all we'd have to do, change the compounding frequency to the payment frequency, we're over it. Okay. So we'll move to that next day, but first, we'll start with ordinary, simple annuities. I don't think there's a set order that you have to say these in. I think you could say simple ordinary annuities. I don't see a reason why not.
So that just means that it's a payment at the end of each payment period that also coincides with the compounding period.
Exactly. So I'll just highlight this as a new section-ish. So if we have n payments, right, then we can just find the future value. So I'm just going to outline the future value and the present value because there's really nothing to talk about, right? We just do it. So in the case of n payments, we find the future value of ordinary simple annuities, bless you, by the future value formula, I'll just steal it from your formula sheet, is the PMT, right? That's the amount of each of these equal payments. Big bracket, little bracket, 1 plus I to the power of n minus 1 over I. And the present value by the present value formula. Present value is the PMT. You'll notice it'll look similar, but it's very different. Right? PMT 1 minus 1 plus I to the negative n all over I. Right. So I'll just make a note here, right? Depending on if we want to know something about the future value or the present value, we'll have to pick the right formula, right? Picking the wrong formula and applying it could be bad news, right? Future value, we're increasing in value. Present value, we're decreasing in value. So, depending on if we want to find I'll say /no, right? There are some scenarios where we know the future value and we want to know the payment amount, for example, right? Then we'd have to use the future value formula, right? The future value or the present value, we will need to pick the appropriate formula. Besides that, not too bad. Now that we know the store function, right? Exactly.
And the negative then exponent, that's or 1 plus 1 over 1 plus I.
Yeah, so it's technically 1 minus 1 over 1 plus I to the power of n. Yeah, exactly. And then all over I. Yeah. What a mess. Okay. Oh, I found a fun thing on your calculator. There's, yeah, I was messing around. Surprise, surprise. There's a memory button over the 0, so second 0. And then you can scroll through what you've stored in all your memories.
Oh, I like that.
Fun, right?
If you ever stop storing something like that.
Yeah, so if you're like, oh, I can't remember where I put it, you can just scroll through. Yeah, I think that was all I found though. Can't remember. I was playing around with it. Okay, let's do an example. Example 204. Okay. So, we do. Don't worry. I'll show you how to do the timeline. Okay. So Martha contributes $10,000 each year to her RSP. Seems reasonable enough. At a rate of interest of 7% per year, how much will she have after 25 years? It's easy. Just do 25 future values. That's all you need to do, guys. Sounds terrible. You don't have to. Don't worry. Okay. But let's see how we draw these timelines for annuities. Because we do have to draw timelines, of course. Let's start it today. And then she's going to go for 25 years. What I want to see is these end ticks, of course. And then I want to see 2 ticks here and 1 tick, at least 1 tick here. Right. So always at least 5 ticks in total. Okay. And between the rest of them, because they're going to be the same, right, you'll just do dot, 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 say, oh, they're all the same. Okay. So if she's making contributions each year, right, we've got 1 year, 2 years, dot, 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 and then 24 years, 25 years. So at a minimum, that's what I want to see. The first, I'm calling it the first 2 ticks and the last 2 ticks, right, starting today. Okay. All right, good. So now, same idea, right? We put the amount underneath for each of these. So here, she's making a payment at year 1, a payment at year 2, a payment at 24 years, and a payment at 25 years. Technically, what we would be doing, right, is just future value 1, future value, blah, 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 right? but that's not what we're gonna show it as. That would get really nasty. Okay. So instead, we're just gonna use this a curly bracket to denote that all these funnel into some future value at 25 years. Okay. You can use a square bracket too, but I think curly brackets are really fun, so fun to draw. So then here, then I can just show that, okay, all these guys are funneling into some future value at 25 years. Okay. How did I know I wanted a future value? Well, because I want to know how much will she have after 25 years. 25 years is in the future, so it's a future value, right? On the right-hand side of the arrow, it's a future value. In general, if we're saving, it's usually going to be calculating a future value. If we're paying off a loan, I'll ask you how much was the loan for. That'll be a present value. So what are we given here? We've got we're just told that the rate is 7% per year. 0.07 per year. So I guess F is 1. Yeah, but that's part of the solutions that I snuck in there. But yeah, it didn't actually say. I guess we just assume. Yeah, all right. Okay. So then I is R over F. 0.07 over 1, which is still 0.07. N is the number of payments. Right. So here, I'm making payments each year for 25 years. Right. So N is just going to be 25. 25 payments. And I put the N on the arrow again, just like we have been doing, just remembering that the N is now payments instead of compoundings, especially because we weren't given a compounding. 1, I guess. And so we're making payments annually, right, every year. And then we're, I guess, compounding every year. So they're the same, right? That's what makes it a simple annuity. Payment and compoundings are the same. Since payments are annual and F is 1, they are the same, which means we have a simple annuity. So it's good to get in the habit of checking, right? How often am I making payments? When am I compounding? Are they the same? Great, then I can ignore that. If not, then we go to that extra step where we adjust it before we do any calculations. Okay, so we've got our payment amount is 10,000. But if we're looking at our future value formula, we need our payment amount, that's 10,000. We have our I, and we have N, which was 25 payments. So we have everything that we need for this formula. So we can find the future value is the PMT square bracket times 1 plus I to the power of N minus 1 over I. So we know our payment amount, right? Each payment is 10,000 times 1 plus I, which we decided was 0.07, to the power of N, which was 25 payments minus 1 over 0.07. If you didn't like the store function yet, you will. 1.07 to the power of 25 minus 1. I guess I'll show my work this one time so you can make sure that your calculator is doing what it should. But usually I would just simplify that whole big bracket. And even then, maybe I'll just go right to the answer, because it's kind of a waste of time to stop and write down your answer. I know that, or your work, I guess, because we're on a roll here. 1.07 to the power of 25 is 5.4274324 minus 1. Don't forget that minus 1 over 0.07 divided by 0.07. So I get 10,000 times 63.249037772. Now multiply by 10,000. We have $632,490.38. That's pretty good. Right? How much did she pay? Right, out of her pocket, she paid 10,000 times 25. Right? So even though she had to pay 10,000 times 25, out of pocket she paid $250,000, but at 25 years, she would have $632,000. I think it sounds like a pretty good deal. If you can muster the 10 grand each year. Ugh. For 25 years. Yeah, if you can finagle a 7% interest rate, let me know. Those were the days. But anyways, so she would have $632,490.38, but paid, right, $250,000 out of pocket. It's a lot of interest. So let's do another example. This one I think is so funny, only because of the names. So 210. Hank borrowed money from Tank. Hank agreed to make yearly payments of $2,500 for 12 years. If Tank charges interest of 13% compounded annually, what was the amount of the loan? So I find that these interest rates are kind of, yeah, well, actually for like your visa, I think is what, around 20%, 19% or something. So 13 would be pretty good in that case, right? So all these interest rates are just kind of weird. Like this is a little bit low. Hers, whatever her name was, Martha. We have to remember their names. It's very important. No. Martha, she got a great rate. Hank, not so much. So, okay. Same idea, right? But like I said, if we're paying back a loan, usually we want to know the loan amount. The loan amount is what you borrowed today, making it a present value, right? So let's draw this out. So today, and then I want to see 1, 2 ticks at the front, 1 tick at the back, dot, dot, dots in the middle, right? Just to indicate that, hey, this actually just happens over and over again. Right? So he's going to make yearly payments, right? So this is good. So yearly payments and it's compounded annually, right? So they're the same, so we don't have to deal with that. That's good. Yeah. So we've got 1 year, 2 years, and he's going to make payments for 12 years. So this would be at 11 years. And he's going to make payments of $2,500, $2,500, $2,500, $2,500. Same idea. All of these payments are going to funnel into some present value today. So I know it was a test, but I saw, so everyone's kind of rushing to get everything done. But I want to see this present value line up with today. Right? If you're just drawing the line to here, because I don't know, something happened, you got tired or whatever. Like, ah, screw this line. Just take it all the way to today. Right? Make sure it's nice and proper. Right? So that present value is going to be how much he borrowed, right? And then had to pay back with these 2,500, taking into account the rate of 13% compounded annually. So here on our arrow, we've got N is 12 payments. We know that R is 0.13, F is 1. So then I'm just going to say is, I can't do it. 0.13. Could you have just said 0.13? Yeah, you can, but I just have a little hang up. I is R over F, even if F is 1. But. Okay, so our present value formula on our formula sheet is the PMT, right? The 2,500 times 1 minus 1 plus I to the negative N all over I. So we've got 2,500 times 1 minus 1 plus 0.13 to the negative N, which was 12, over 0.13. Like I said, I think I'm just gonna plow through this, no stopping. 1.13 to the power of 12 negative equals 1 minus that guy divided by 0.13. Sure, I'll do one stop. 2,500 times 5.9176 47017 times 2,500. Did you do 1 minus that? So in total, I get 14,794 and 12 pennies. How much did he pay though? 2,500 times 12, 30,000. What the? So the loan was $14,794.12, but he paid $2,500 times 12 is $30,000. That sounds terrible. But that's loans for you, I guess. On that sober note, sober, somber,
Here we go.
we'll end. Have a great long weekend, you guys. Oh, no class on Tuesday, right? Yeah. Yeah. Let me just end this here. I'll end it and put the notes back up.